Picture this. You're standing in your backyard on a clear night, looking up at the stars scattered across the darkness like diamonds on velvet. You point in any direction and imagine traveling in a straight line, never stopping, never turning. Where would you end up? Would you eventually hit a wall? Find an edge where space simply stops? Or would you keep going forever, through an endless expanse that has no beginning and no end? This question has haunted humanity for millennia, and the answer might be stranger than you think. Hello, and welcome to a journey through one of the most profound mysteries our universe has to offer. Tonight, we're going to explore the boundaries of everything that exists, or perhaps the absence of boundaries altogether. Before we begin, take a moment to settle in wherever you are. Maybe you're listening at home, wrapped in the comfort of familiar surroundings. Maybe you're somewhere else entirely, in a place that's new to you. Either way, you're here now, and that's what matters. If this kind of gentle exploration into the deepest questions of existence appeals to you, if you find comfort in wondering about things larger than ourselves, I'd be grateful if you subscribe to the channel. It helps this quiet corner of curiosity find others who might be searching for the same kind of thoughtful reflection. And now, let's step together into the vast unknown, where the very concept of endings and beginnings takes on meanings we've barely begun to understand. When we talk about space ending, we first have to understand what we mean by space itself. It's easy to think of space as just the emptiness between things, the void that separates planets and stars. But space is much more than that. It's the very fabric of reality, the stage upon which every cosmic drama unfolds. And like any stage, it raises the question, where do the curtains fall? The observable universe, the sphere of everything we can potentially see from Earth, extends roughly 46.5 billion light-years in every direction. That's not a typo. Even though the universe is only about 13.8 billion years old, the expansion of space itself has stretched that original light to reach us from much greater distances. Imagine throwing a ball to a friend who's walking away from you. By the time the ball reaches them, they're much further away than when you threw it. Light from distant galaxies works similarly, travelling through expanding space to reach our telescopes. But here's where it gets interesting. That observable boundary isn't a wall or an edge in any meaningful sense. It's simply the limit of what we can see, defined not by the structure of space itself, but by time. Light from beyond that boundary simply hasn't had enough time to reach us yet. It's like standing on a hill and seeing to the horizon. You know there's more landscape beyond what you can see, but your view is limited by the curvature of the Earth and the clarity of the air. This creates a profound realization. Our entire observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, might be just a tiny speck in something incomprehensibly larger. If space is infinite, then everything we can see, everything we've ever studied or wondered about, represents essentially 0% of what actually exists. The implications are staggering. In an infinite universe, every possible arrangement of matter and energy would exist somewhere. Not just similar arrangements, but exact duplicates. There would be another galaxy identical to the Milky Way, another solar system identical to ours, another Earth where someone exactly like you is listening to these exact words. The mathematics of infinity demand it. Given infinite space and a finite number of ways to arrange matter, every possible configuration must occur, and occur infinitely many times. But infinity is a concept that quickly becomes difficult to grasp. We can understand large numbers, even incomprehensibly large ones, but infinity isn't just a very large number. It's a fundamentally different kind of thing altogether. It's the point where our intuitions break down, and mathematics takes over, revealing truths that feel almost mystical in their implications. The question of whether space ends is intimately connected to its shape. Just as a sphere has no edges but is still finite, space itself might be curved in ways that give it boundaries without edges, or no boundaries at all. Recent observations from satellites studying the cosmic microwave background radiation, the afterglow of the Big Bang itself, have revealed something remarkable about the geometry of our universe. Space appears to be flat, at least within our observable region, to an extraordinary degree of precision. This flatness has profound implications for the question of cosmic boundaries. A flat universe presents us with two primary possibilities. It could extend infinitely in all directions, like an endless sheet of paper, or it could be finite but wrap around on itself, like a sheet of paper formed into a cylinder or folded into more complex shapes. The analogy breaks down in 3 dimensions, but mathematically, space could curve back on itself in ways that create a finite volume without any edges or boundaries. Imagine an ant walking on the surface of a sphere. From the ant's perspective, the surface appears flat and extends in all directions. The ant could walk forever without encountering an edge, yet the surface is clearly finite. Our 3-dimensional space could work similarly, curved through higher dimensions in ways that create a finite but unbounded cosmos. The possibility of a finite universe raises intriguing questions about repetition and pattern. If space is finite but larger than our observable region, we might theoretically be able to see around it, observing the same galaxies from multiple directions as their light takes different paths through the curved geometry. These would appear as cosmic mirages, duplicate images of the same objects, separated by vast distances. The search for such patterns represents one of the few ways we might directly determine whether our universe has boundaries. But the measurements suggest something else entirely. If our universe is indeed finite, it must be at least 400 times larger than what we can observe. The cosmic horizon that defines our view extends 46.5 billion light-years in every direction, creating a sphere of observation with a diameter of 93 billion light-years. If space curves back on itself, that curvature operates on scales so vast that it remains invisible to our most sensitive instruments. This raises a humbling thought. We might be living inside something finite, bounded, and knowable, yet still be utterly incapable of perceiving those boundaries. Like bacteria in a drop of water, unaware that their entire world has edges just beyond their ability to detect. We might exist within constraints we can't even imagine. The story becomes even more complex when we consider the dynamic nature of space itself. The universe isn't static, it's expanding, and that expansion is accelerating. Dark energy, a mysterious force that makes up roughly 68% of everything that exists, is pushing space apart at an ever-increasing rate. This expansion doesn't mean galaxies are flying through space away from each other. Rather, space itself is growing, carrying galaxies along with it like raisins in rising bread dough. The implications for cosmic boundaries are profound. Even if space is infinite now, what does that mean in a context of eternal expansion? The theory of eternal inflation suggests that our observable universe might be just one small bubble in an infinite sea of space that's constantly expanding and creating new regions. In this model, inflation never completely stops everywhere at once. Instead, it creates a fractal structure where some regions, like ours, stop inflating and form stable pockets of spacetime, while other regions continue to expand exponentially. If eternal inflation is correct, then the question of whether space ends becomes almost meaningless. Space wouldn't just be infinite, it would be infinitely generating new space, creating an ever-growing expanse of reality that includes every possible variation of physical laws and constants. Our universe, with its specific properties that allow for stars, planets, and life, would be just one possibility among infinite others. But recent theoretical work has challenged aspects of eternal inflation, suggesting that the process might be more limited than originally thought. The late Stephen Hawking's final research proposed that while the multiverse might still exist, it could be far smaller and more structured than the infinite fractal originally predicted. This work attempts to make the theory more testable and less dependent on concepts of actual infinity that create mathematical paradoxes. The expansion of space also creates another kind of boundary, a horizon beyond which we will never be able to see, no matter how long we wait. Due to the accelerating expansion driven by dark energy, there's a maximum distance from which light will ever be able to reach us. Galaxies beyond this boundary are already receding faster than light can travel, through expanding space, creating regions that are forever beyond our reach. This future horizon extends roughly 62 billion light-years from Earth. Beyond that distance, objects are carried away by expansion faster than their light can make progress toward us. It's a one-way boundary in time, ensuring that there are parts of the universe we will never be able to observe, regardless of how advanced our technology becomes. In a sense, this expansion-driven horizon creates a kind of ending to space from our perspective. Not because space itself terminates, but because the very geometry of space-time isolates us from distant regions. We exist within an island of causality, able to influence and be influenced only by objects within a finite volume, even if space extends infinitely beyond that volume. The acceleration of this expansion means our cosmic neighborhood is actually shrinking in terms of what we can interact with. Galaxies that we can see today will eventually disappear beyond our horizon, carried away by expansion until their light can no longer reach us. Future civilizations might find themselves in a much lonelier universe, able to observe only their immediate galactic neighborhood. This creates a poetic irony. As space potentially grows without bound, our ability to explore and understand it becomes increasingly limited. We might live in an infinite cosmos, yet find ourselves progressively isolated within an ever smaller sphere of influence and observation. As we continue our journey through these cosmic mysteries, we'll next explore what lies beyond even the concept of boundaries, where the very nature of reality itself might be more strange and wonderful than we've yet imagined. There's something almost mystical about the concept of nothingness, isn't there? We use the word so casually in everyday conversation, but when we try to apply it to the cosmos, it becomes slippery, elusive, like trying to hold water in cupped hands. What would it mean for space to truly end? What would lie beyond that ending? The human mind struggles with genuine emptiness. Even when we imagine a perfect vacuum, we picture darkness, as if darkness itself were something rather than the absence of light. But darkness requires space to exist within. True nothingness would be the absence of space itself, the absence of any arena in which things could exist or not exist. It's a concept so foreign to our experience that language itself begins to fail us. Consider this thought experiment. Imagine you're traveling through space in a perfect straight line, moving beyond the farthest galaxy, beyond the edge of our observable universe, beyond any conceivable boundary. In a finite universe, what would you encounter at the limit? A wall? But walls are made of something, and that something exists in space. A barrier of any kind would itself be a part of the universe, not its ending. Perhaps the answer lies not in what you would encounter, but in what the very concept of travelling would mean in such a context. In a truly finite universe, space itself might curve back on itself so completely that your straight-line journey would eventually bring you home. Like an ancient sailor who feared falling off the edge of the world, but instead found himself approaching familiar shores from the opposite direction. This brings us to one of the most elegant solutions to the boundary problem, the idea that space might be finite yet unbounded. Picture the surface of Earth. It's clearly finite in area, yet an ant walking on it would never find an edge. The ant could walk forever, exploring new territories, yet always remain within a bounded system. Now imagine this principle extended to three-dimensional space. curved through dimensions we can't directly perceive. The mathematics of such spaces are well understood, even if the reality is impossible to visualize. A hypersphere, the three-dimensional analogy of a sphere's surface, could contain all of space within a finite volume while still having no boundaries or edges. Every direction would be equally valid, every path potentially infinite, yet the total space would be measurably finite. But here's where the mystery deepens. Recent observations suggest that if our universe is indeed finite in this way, it must be so large that its curvature is virtually undetectable. The cosmic microwave background radiation, that ancient light from when the universe first became transparent, shows no signs of the repeating patterns we might expect in a smaller curved space. If space does curve back on itself, it does so on scales that dwarf even our observable universe. This creates a peculiar situation. We might live in a finite cosmos, yet be forever unable to detect its boundaries. Like inhabitants of a vast sphere so large that any measurable portion appears perfectly flat, we could be surrounded by curvature operating on scales beyond our comprehension. As we probe deeper into the nature of space and its potential boundaries, we encounter something unexpected. The quantum realm, where the very fabric of reality behaves in ways that challenge our deepest assumptions about existence itself. At the smallest scales, space isn't the smooth, continuous expanse it appears to be. Instead, it's a seething foam of quantum fluctuations, where virtual particles pop in and out of existence in intervals so brief they seem to mock our understanding of time. These quantum fluctuations aren't just theoretical curiosities, they're measurable, observable phenomena that affect everything from the behavior of atoms to the expansion of the universe itself. They suggest that even empty space isn't truly empty, but is instead filled with a constant dance of creation and annihilation, a symphony of existence playing at frequencies beyond human perception. This quantum nature of space has profound implications for the question of cosmic boundaries. If space itself is quantized, made up of discrete units rather than being infinitely divisible, then perhaps the question of whether it ends is like asking whether numbers end. Numbers are infinite, yet each number is distinct, separate from its neighbours by finite gaps. Could space work similarly, extending infinitely, yet made up of fundamental units that give it structure and definition? The concept of vacuum decay adds another layer to this quantum mystery. In quantum field theory, what we think of as empty space might not be in its most stable state. Like a ball balanced on a hilltop, our vacuum might be metastable, temporarily stable but capable of rolling down to a lower, more stable state. If this were to happen, it would fundamentally alter the laws of physics themselves, creating a bubble of new reality that would expand at the speed of light, rewriting the nature of existence as it grew. The measurements of the Higgs boson, that fundamental particle responsible for giving mass to all other particles, suggest we might be living right at the edge of stability. Our universe appears to exist in a delicate balance between absolute stability and metastability. It's as if reality itself is poised on a knife's edge, stable enough to allow the complex structures we see around us, yet potentially fragile enough to transform completely under the right conditions. This quantum perspective transforms the question of space's boundaries. Instead of asking whether space ends in some distant location, we might ask whether the fundamental nature of space itself could change, creating boundaries not of position, but of possibility. A region where different physical laws apply would be as foreign to us as a different universe entirely. Recent experiments with ultra-cold atoms have provided the first direct observations of vacuum decay processes, albeit on microscopic scales. These experiments show how metastable states can suddenly collapse into more stable configurations, creating bubbles of new physics that expand and consume the old. While these laboratory demonstrations involve tiny systems lasting mere fractions of a second, They provide a glimpse into processes that might operate on cosmic scales over cosmic timescales. When we contemplate infinite space, we're not just imagining a very large container. We're considering something that transcends all human categories of size and scale. Infinity isn't just bigger than anything we can measure, it's categorically different from any finite quantity, no matter how large. In an infinite universe, mathematics tells us something remarkable and unsettling. Every possible arrangement of matter and energy must occur, and must occur infinitely often. This isn't speculation, it's a logical consequence of combining infinite space with finite possibilities. If there are only so many ways to arrange atoms in a given volume, and if space extends infinitely, then every possible arrangement must exist somewhere. This leads to what cosmologists call the quantum copy problem. In an infinite universe, there would be another region of space, perhaps unimaginably distant, where matter has arranged itself into an exact duplicate of our solar system, our Earth, and even ourselves. Not similar arrangements, but perfect atomic-level copies living through identical experiences, thinking identical thoughts. The probability of such exact duplication is vanishingly small, but in infinite space, even vanishingly small probabilities become certainties. Somewhere out there, according to this reasoning, is another you, listening to these same words, contemplating the same mysteries, and another in infinite repetition. But infinity creates even stranger possibilities. In an infinite universe, there would be regions where the laws of physics appear to be different, not because they actually are, but because random fluctuations have created pockets of extraordinary organization or chaos. There would be regions where entropy has spontaneously decreased, where broken things have randomly reassembled themselves, where the impossible has become inevitable through sheer statistical weight. These ideas push our understanding to its limits. How do we make sense of a cosmos where every story that could be told is being lived out somewhere, where every choice you didn't make has been made by another version of you in some distant region of space, where every possible variation of history, no matter how unlikely, is actually unfolding? Some theorists have suggested that the observable universe represents just one patch in this infinite expanse, a region where certain physical constants happen to have values that allow for stable matter, stars, planets, and life. Other patches might have different values, creating realms where our familiar physics breaks down entirely. We exist in a patch suitable for our kind of existence, not because we're special, but because that's the only kind of patch where observers like us could evolve to ask these questions. This anthropic reasoning suggests that the apparent fine-tuning of our universe's physical constants might not require a designer or special explanation. In an infinite cosmos with varying physical laws, every possible combination would exist somewhere. We find ourselves in a region compatible with our existence, for the same reason fish find themselves in water. It's the only environment where they could survive to notice their surroundings. Yet this explanation comes with a cost. If our physical constants are just random variations in an infinite space, then science itself becomes a local phenomenon. The laws we discover might be no more universal than local weather patterns, applicable only within our particular patch of reality. As our cosmic perspective expands, so too does our understanding of time's role in shaping spatial boundaries. The universe isn't just expanding, that expansion is accelerating, driven by the mysterious dark energy that makes up more than 2/3 of everything that exists. This acceleration creates a kind of temporal boundary to space, defining not just what we can see, but what we will ever be able to see. The cosmic event horizon, currently located about 16 billion light-years away, represents the boundary beyond which events occurring now will never be observable from Earth, no matter how long we wait. Galaxies beyond this horizon are receding so rapidly that even light they emit today will never catch up to us through the expanding space between us. This creates a sobering picture of the cosmic future. The galaxies we observe today will gradually disappear from view as expansion carries them beyond our event horizon. Future astronomers, working billions of years from now, might find themselves in a much lonelier universe, able to observe only their local group of gravitationally bound galaxies, while the rest of the cosmos fades into invisibility. In this far future, the question of whether space ends might become unanswerable, not because of any limitation in our theoretical understanding, but because the evidence itself will have been carried away by expansion. Future scientists might rediscover the same questions we're exploring now, but with far less information to guide their investigations. The acceleration of expansion also affects the ultimate fate of space itself. In one scenario, called the Big Rip, the expansion could eventually become so violent that it tears apart not just galaxies and stars, but atoms themselves. Space would expand so rapidly that even the fundamental forces holding matter together would be overcome, leaving behind only isolated particles in an ever-growing void. Alternatively, the expansion might continue more gently, leading to what cosmologists call heat death, a state where the universe reaches maximum entropy, with all energy evenly distributed and no temperature differences to drive the processes we associate with life and structure. In this scenario, space might continue indefinitely, but it would be a cold, dark, empty expanse where nothing interesting could happen. These distant futures remind us that the question of whether space ends might be inseparable from the question of whether time ends. Even infinite space might become effectively finite if expansion isolates every region from every other, creating countless isolated islands of causality in a sea of unreachable distance. Yet there's something beautiful in contemplating these vast timescales. Long after our sun has exhausted its fuel and our galaxy has merged with Andromeda, long after the last stars have died and the last black holes have evaporated through Hawking radiation, space itself might continue, carrying within its expanding geometry the mathematical relationships and physical laws that once gave rise to complexity, consciousness, and wonder. Perhaps that's where our answer lies. Space might not end in any location we could point to, but it might evolve, transform, and ultimately transcend the very categories we use to understand it. The boundary might not be a place but a moment, not a wall but a transformation into something so different from our current reality that the question itself becomes meaningless. As we drift deeper into these cosmic contemplations, we find ourselves approaching another profound mystery, one that connects the vastness of space to the intimate experience of time itself, and asks whether the moments we experience might be just as infinite and mysterious as the cosmos that contains them. Time has a curious relationship with emptiness, doesn't it? When you sit in a quiet room late at night, the silence feels almost tangible, as if the absence of sound has weight and presence. Space works similarly, carrying within its apparent emptiness the memory of everything that has ever happened within it. Every star that has died, every galaxy that has formed, every moment of cosmic history leaves its trace in the fabric of space-time itself. The cosmic microwave background radiation serves as space's memory bank, a faint glow that permeates every cubic centimetre of the universe. This ancient light, released when the cosmos was only 380,000 years old, carries information about the universe's earliest moments. It's as if space itself remembers its youth, holding on to those primordial photons like an old photograph tucked away in a drawer. But this memory extends beyond light. Gravitational waves, ripples in space-time itself, carry information about some of the most violent events in cosmic history. When two black holes collide billions of light years away, they send shudders through the very geometry of space, stretching and compressing the distances between objects in ways so subtle they can only be detected by our most sensitive instruments. These waves travel at the speed of light, but unlike electromagnetic radiation, they pass through matter almost unimpeded. A gravitational wave that began its journey when the universe was young could still be washing over us today, carrying within its oscillations the story of ancient cosmic catastrophes. In a very real sense, space never forgets anything that happens within it. This creates a profound possibility. If space is infinite, then it contains not just infinite matter and energy, but infinite information. Every possible story, every conceivable sequence of events would be encoded somewhere in the gravitational field, fluctuations and electromagnetic radiation that fill the cosmos. The universe would be not just a collection of objects in space, but a vast library of experiences, with every possible narrative written in the language of physics. The implications reach beyond science into something approaching the mystical. In an infinite cosmos filled with infinite information, consciousness itself might be just another pattern that space learns to remember. The neurons firing in your brain as you contemplate these ideas, the electrical patterns that constitute your thoughts and memories, might be part of a much larger information processing system that extends throughout space itself. Some theorists have suggested that consciousness might be a fundamental feature of the universe, not something that emerges from complex arrangements of matter, but something that space itself is capable of. If information can be stored in gravitational fields and quantum fluctuations, then perhaps the boundary between mind and cosmos is less clear than we imagine. This perspective transforms the question of space's boundaries once again. Instead of asking whether space ends somewhere, we might ask whether there are limits to what space can remember, experience, or know. Could there be regions so distant that their information can never reach us, creating boundaries not of space, but of knowledge itself? Mathematics, that most abstract of human languages, becomes strangely concrete when applied to the cosmos. The equations that describe space-time aren't just symbols on a blackboard. They're instructions that reality follows with perfect fidelity. Every gravitational interaction, every quantum fluctuation, every expansion of space itself obeys mathematical relationships that we can write down, study, and understand. This mathematical nature of reality suggests something profound about the question of space's boundaries. In mathematics, infinity isn't just a very large number. It's a precisely defined concept, with specific properties and behaviors. Mathematical infinities can be compared, manipulated, and understood in ways that reveal deep truths about the structure of reality. Consider the mathematician Georg Cantor's revolutionary discovery that there are different sizes of infinity. The infinity of counting numbers is smaller than the infinity of real numbers, which is smaller than the infinity of possible functions, and so on. This hierarchy of infinities suggests that if space is infinite, we need to ask, which kind of infinity are we dealing with? If space contains infinitely many discrete locations, that might be one kind of infinity. But if space is also infinitely divisible, containing infinitely many points between any two locations, that would be a much larger infinity. The mathematical structure of space itself might determine not just whether it's infinite, but how infinite it is. These mathematical considerations aren't merely abstract, they have physical consequences that we can observe and measure. The flatness of space, revealed through precise measurements of the cosmic microwave background, corresponds to specific mathematical relationships between the geometry of spacetime and its matter and energy content. Einstein's field equations don't just describe how matter curves space, they define what space is at the most fundamental level. The relationship between mathematics and physical reality runs so deep that some physicists have proposed we live in a mathematical universe where physical objects are literally mathematical structures rather than things described by mathematics. In this view, particles, forces, and fields aren't made of some underlying substance. They are the mathematical relationships themselves, existing as pure information. If this mathematical universe hypothesis is correct, then asking whether space ends is like asking whether mathematics ends. And mathematics, as far as we know, extends infinitely in all directions, containing every possible logical structure and relationship. In a truly mathematical cosmos, space wouldn't just be infinite, it would be necessarily infinite, unable to end because mathematical truth itself is unbounded. This creates a beautiful symmetry. Consciousness, which seems to be the universe's way of understanding itself, uses mathematics to probe the deepest questions of existence. We are mathematical structures, contemplating mathematical structures, using mathematical tools to ask whether the mathematical space we inhabit has boundaries. The answer, if it exists, might be written in the same mathematical language that describes quantum mechanics, relativity, and the expansion of space. Perhaps the boundary between finite and infinite space isn't a location, but an equation. Not a place we could visit, but a relationship we could discover. There's a particular kind of quiet that exists between radio stations, isn't there? That soft static that fills the gaps between human voices, between signals crossing the electromagnetic spectrum. Space has its own version of this silence, a background hum of radiation and particle interactions that pervades every region of the cosmos. But this cosmic background isn't empty silence, it's filled with information, with stories written in wavelengths of light and frequencies of vibration that span the entire electromagnetic spectrum. Radio waves from distant galaxies, X-rays from black hole accretion disks, gamma rays from stellar explosions, infrared radiation from clouds of interstellar dust. Every frequency tells a different chapter of the cosmic story. The question of space's boundaries becomes intimately connected to this electromagnetic symphony. If space truly ends somewhere, what would happen to light travelling toward that boundary? Would it simply stop, creating a wall of accumulated radiation? Would it reflect back, creating standing wave patterns that we might detect? Or would it disappear into something beyond space, carrying its energy and information into realms we can't imagine? The cosmic web, that vast network of dark matter filaments connecting galaxies across billions of light years, might provide clues about space's ultimate structure. These filaments, invisible except through their gravitational effects on visible matter, create the largest known structures in the universe. They form a kind of cosmic skeleton, with galaxies and galaxy clusters strung along them like lights on an impossibly vast Christmas tree. If space is finite, this cosmic web would eventually close back on itself, creating patterns and connections that might be detectable through careful observation. Galaxy surveys that map the three-dimensional structure of the universe are essentially creating maps of space itself, charting the distribution of matter and energy across cosmic scales. Recent observations have revealed that the cosmic web extends as far as we can see, showing no signs of repetition or closure. The patterns appear to be statistically uniform in all directions, consistent with either an infinite universe or a finite one so large that its boundaries lie far beyond our observational reach. But there's something haunting about the spaces between these cosmic structures, the vast voids that contain almost no matter or energy. These cosmic deserts, some hundreds of millions of light years across, are among the emptiest regions known to exist. In these voids, space approaches its purest form, nearly free of the matter and radiation that usually fill it. What exists in these empty regions might be the closest we can come to understanding what space itself is like, when stripped of everything we usually think of as something. Yet even these voids aren't truly empty. They contain dark energy, the mysterious force driving cosmic expansion. They're crossed by cosmic rays and filled with the faint glow of the cosmic microwave background. Perhaps true emptiness, the kind of nothingness that might exist beyond the boundaries of space, is something qualitatively different from even the emptiest regions within our universe. It might be the absence not just of matter and energy, but of the possibility of matter and energy. the absence of the mathematical relationships that define physical existence itself. We live our lives in 3 dimensions of space, moving freely forward and backward, left and right, up and down. These dimensions feel so fundamental to our experience that it's difficult to imagine reality could be otherwise. Yet modern physics suggests that our familiar 3-dimensional space might be just a projection of something far more complex and beautiful. String theory, one of the most ambitious attempts to unify all known forces and particles, requires space to have not 3 dimensions, but 10 or 11. The extra dimensions are supposedly curled up so tightly that we can't perceive them directly, but they influence the behavior of matter and energy in ways that might be detectable through careful experiments. If these hidden dimensions exist, they transform the question of space's boundaries entirely. Instead of asking whether 3-dimensional space ends somewhere, we need to ask about the topology of a much higher dimensional space that contains our familiar reality as just one small aspect of its structure. Imagine a garden hose viewed from a great distance. It appears to be a 1-dimensional line, but up close, you can see that it has additional dimensions curled around its central axis. Similarly, what we perceive as 3-dimensional space might be like the surface of that hose, with additional dimensions curled up at every point in ways too small for us to detect. The boundaries of such a higher dimensional space would be unimaginably complex. Instead of simple edges or walls, there might be topological features that have no analogy in our 3-dimensional experience. The space might fold back on itself through dimensions we can't perceive, creating connections between distant regions that bypass our familiar geometry entirely. Some versions of string theory suggest that our entire 3-dimensional universe might be a brane, a lower dimensional surface embedded in a higher dimensional space called the bulk. Other branes might exist nearby in the extra dimensions, carrying their own versions of physics and their own collections of matter and energy. The boundaries between these branes might be the closest thing to cosmic edges that actually exist. The mathematics of these higher dimensional spaces are elegant and precise, but their physical interpretation remains deeply mysterious. We can calculate how particles would behave in 10-dimensional space, but we can't visualize what such a space would look like, or what it would mean to travel through it. This mathematical richness suggests that reality might be far stranger and more wonderful than our 3-dimensional experience suggests. The question of whether space ends might be like asking whether a shadow has depth. The shadow exists and has measurable properties, but the real structure lies in dimensions the shadow can't reveal. Recent experiments at particle accelerators have searched for signs of these extra dimensions by looking for particles that might escape our 3-dimensional brane and travel through the bulk. So far, no such evidence has been found, but the search continues, driven by the possibility that we might be living on the surface of something much deeper and more extensive than we ever imagined. If extra dimensions exist, they might provide a natural resolution to the infinity problem. Instead of space extending infinitely in our familiar 3 dimensions, it might be finite, but curved through higher dimensions in ways that create the appearance of infinity from our limited perspective. Dark energy, that mysterious force responsible for the accelerating expansion of space, makes up roughly 68% of everything that exists. Yet we know almost nothing about what it actually is. It's invisible, undetectable, except through its gravitational effects, and seemingly uniform throughout space. It's as if the vacuum itself has weight, pushing space apart with a constant, relentless pressure. This dark energy might hold the key to understanding space's ultimate fate and extent. If it remains constant, the expansion of space will continue to accelerate, eventually carrying distant galaxies beyond our observational horizon. If it increases over time, the expansion could become so violent that it tears apart not just large-scale structures, but atoms themselves, leading to the Big Rip scenario, where space expands so rapidly that even the forces holding matter together are overwhelmed. Alternatively, dark energy might be unstable, subject to quantum fluctuations that could cause it to decay into other forms of energy. Such a phase transition would be catastrophic, creating a bubble of altered physics that would expand at the speed of light, transforming the fundamental nature of space itself as it grew. The stability of dark energy is intimately connected to the stability of space itself. Quantum field theory suggests that what we think of as empty space is actually filled with virtual particles that pop in and out of existence in time frames so brief they challenge our understanding of reality. These quantum fluctuations give empty space an energy density that should be enormous, yet observations show that it's incredibly small. This discrepancy, known as the cosmological constant problem, represents one of the greatest unsolved mysteries in physics. The quantum calculation and the observed value differ by a factor of 10^20, making it the worst prediction in the history of science. Yet this mismatch might be telling us something profound about the nature of space itself. Perhaps the energy density of empty space is balanced by some unknown mechanism that keeps it stable. Or perhaps we live in a universe where this energy density happens to be small enough to allow for the existence of matter and structure. In an infinite multiverse, regions with every possible value of dark energy would exist, and we naturally find ourselves in a region compatible with our existence. The quantum nature of space raises another possibility, that space itself might be quantized, made up of discrete units rather than being continuously divisible. At the Planck scale, roughly 10^35 meters, quantum effects become so strong that our usual concepts of space and time begin to break down. Below this scale, space might not exist in any meaningful sense, replaced by something more fundamental that gives rise to spatial relationships only at larger scales. If space is quantized, then asking whether it's infinite becomes like asking whether there are infinitely many pixels on a screen. The question might have a definite answer, but finding it would require understanding the fundamental structure of reality at scales far beyond our current ability to probe. There's something profound about the way empty space seems to mirror our own consciousness. Both are invisible containers that give meaning to everything they hold, yet remain mysteriously elusive when we try to examine them directly. Just as consciousness seems to be everywhere in our experience, yet nowhere we can point to, space permeates everything, yet remains fundamentally unknowable in its true nature. This parallel isn't merely poetic. Some of the deepest questions in physics and neuroscience involve understanding how complex patterns of information can give rise to unified, coherent experiences. In the brain, billions of neurons create the singular experience of consciousness. In the cosmos, quantum fields and gravitational interactions create the unified fabric of space-time. The holographic principle, emerging from studies of black hole physics, suggests that all the information in a volume of space might be encoded on its boundary. Just as a hologram can store a three-dimensional image on a two-dimensional surface, the universe might store all its information on a distant boundary that we can never directly observe. If the holographic principle is correct, then our three-dimensional experience of space might be a kind of projection from information stored on a two-dimensional surface surrounding us. The question of whether space ends would then become a question about the geometry of this information storage surface. This creates a beautiful symmetry. Just as consciousness seems to emerge from but transcend the neural patterns that create it, space might emerge from but transcend the information patterns encoded on its boundary. We would be living inside a kind of cosmic consciousness, experiencing reality from within an information processing system of unimaginable complexity and scale. The anthropic principle takes on new meaning in this context. If consciousness and cosmos are reflections of each other, then the apparent fine-tuning of physical constants might not be a coincidence, but a necessity. A universe capable of giving rise to consciousness might need to have exactly the properties we observe, not because of design or selection, but because consciousness and physical law are different aspects of the same underlying information structure. Recent work in quantum computing and information theory has begun to reveal deep connections between information, entropy, and the geometry of spacetime. The amount of information that can be stored in a region of space appears to be limited by its surface area rather than its volume, suggesting that space itself might be emergent from more fundamental information theoretic processes. These ideas point toward a resolution of the infinity problem that's both scientifically rigorous and philosophically satisfying. If space emerges from information, then its extent would be determined by the information processing capacity of the underlying system. The universe might be finite, not because it has boundaries, but because there's a limit to how much information can be coherently organized into spatial relationships. In this view, asking whether space ends becomes like asking whether a story ends. Stories can be finite yet complete, bounded yet satisfying, limited yet meaningful. Perhaps space works similarly, creating through its very limitations the conditions necessary for structure, consciousness, and wonder. As we near the end of our cosmic journey, we find ourselves confronting the most profound question of all. Not whether space ends, but what it means for conscious beings, like ourselves, to exist within whatever space contains us. The answer might be waiting in the quantum foam, in the dark energy, in the mathematical relationships that govern reality itself. Or perhaps the answer is simpler, hidden in the very fact that we can ask the question at all. Soon we'll explore another mystery equally profound and equally close to home. The strange relationship between our planet and its faithful companion, and what recent discoveries about their dance might reveal about the forces that shape our world. How the moon controls the ocean, and what scientists just discovered will shock you. Sub-E, sleep documentary. Perhaps the most remarkable thing about space isn't whether it ends, but how it contains within itself every possible scale of existence, from the quantum foam that bubbles beneath reality to the vast cosmic web that connects galaxies across billions of light years. Each scale reveals different truths, different mysteries, different ways of understanding what it means for something to exist within the fabric of everything. At the smallest scales we can probe, space becomes uncertain, probabilistic. The Heisenberg uncertainty principle tells us that at quantum scales, we cannot simultaneously know both the position and momentum of a particle with perfect precision. But this isn't just a limitation of our measuring instruments, it's a fundamental property of reality itself. Space at the quantum level doesn't have definite locations, only probabilities, clouds of possibility that collapse into specific positions only when observed. This quantum fuzziness suggests that space might not be the solid foundation we imagine it to be. Instead, it might be more like a statistical average, a smooth approximation that emerges from countless quantum interactions. Just as a photograph appears smooth from a distance, but reveals individual pixels when examined closely, space might appear continuous at human scales, while being fundamentally granular at the smallest possible scales. The implications are profound. If space is made of discrete units, quantum pixels of reality, then it cannot be infinitely divisible. There would be a smallest possible distance, a fundamental grain size below which the concept of space loses meaning. This quantum granularity might provide a natural cutoff to infinity, suggesting that even in an infinite universe, the infinity would be countable rather than uncountable, discrete rather than continuous. At the other extreme of scale, space reveals structures so vast they challenge our ability to comprehend them. The cosmic web, with its filaments of dark matter stretching across hundreds of millions of light years, creates patterns that repeat at scales larger than anything we can observe directly. Galaxy clusters, superclusters, and the vast voids between them form a hierarchy of structure that extends to the very limits of our observational reach. These larger structures in the universe provide another lens through which to examine the question of cosmic boundaries. If space is finite, then the cosmic web must eventually close back on itself, creating topological connections that might be detectable through careful statistical analysis. Alternatively, if space is infinite, then the web extends forever, creating an endless tapestry of matter and energy woven through dimensions we can barely imagine. The transition between these scales, from quantum to cosmic, happens gradually, each level of organization emerging from the interactions of smaller components. Atoms form from quantum fields, molecules from atoms, cells from molecules, organisms from cells, ecosystems from organisms, planets from countless organisms and their environments, solar systems from gravitational interactions, galaxies from stellar formation, and galaxy clusters from gravitational attraction across cosmic time. At each level, new properties emerge that couldn't have been predicted from understanding the lower levels alone. Consciousness emerges from neural networks, but you can't find consciousness by examining individual neurons. Similarly, the large-scale structure of space emerges from quantum interactions, but you can't understand cosmic geometry by studying quantum mechanics alone. This emergence suggests that the question of space's boundaries might have different answers at different scales. Space might be finite when viewed from a quantum perspective, discrete and granular. It might be infinite when viewed from a relativistic perspective, curved and continuous. And it might be something else entirely when viewed from scales we haven't yet learned to explore. The relationship between these scales also reveals something beautiful about the nature of existence itself. Every atom in your body was forged in the nuclear furnaces of ancient stars, scattered through space by stellar explosions, and eventually gathered into the solar system that became your home. You are literally made of star stuff, arranged in patterns complex enough to contemplate the cosmos that created you. This cosmic recycling extends beyond individual atoms to entire structures. Galaxies merge and separate across cosmic time, their stars redistributed into new configurations. Even black holes, those ultimate gravitational prisons, eventually evaporate through Hawking radiation, returning their information to the universe in forms we're only beginning to understand. And so we find ourselves at the end of our journey, through the infinite and the finite, through the quantum foam and the cosmic web, through dimensions we can see and others we can only imagine. We've travelled from the smallest possible scales of reality to the largest structures in the known universe, asking always the same fundamental question: does space end? Perhaps the most honest answer is that we don't know, and perhaps we never will. But in the asking, in the wondering, in the careful observation and mathematical exploration, we've discovered something even more profound than a simple yes or no. We've discovered that the universe is stranger, more beautiful, and more mysterious than our ancestors could have dreamed. Whether space extends infinitely in all directions or curves back on itself through dimensions we can't perceive, whether it's made of discrete quantum units or flows as a continuous mathematical structure, whether it emerged from eternal inflation or will someday transform into something unrecognizable, one thing remains constant. We are here now, conscious and curious, able to ask these questions at all. In a cosmos that might contain infinite copies of every possible story, the story you're living right now, the thoughts you're thinking as you listen to these words, the wonder you feel when you look up at the night sky, all of it matters. Not because it's unique in an infinite expanse, but because it's real, immediate, and yours to experience. The boundary between finite and infinite space might forever remain beyond our reach, but the boundary between wonder and indifference, between curiosity and complacency, between connection and isolation, those boundaries we can choose to cross every day. and in crossing them, we become part of the universe's way of understanding itself. Conscious patterns in the fabric of space-time, asking questions that echo across the cosmos, whether it ends or continues forever. Thank you for taking this journey with me through the deepest mysteries our universe has to offer. Rest well, and remember that tomorrow brings new opportunities to wonder, to explore, and to find meaning in the vast expanse that surrounds us all.